Hello, it is time for the protein chapter. Now, I'm excited because we have a lot of information to give, a lot of myths to dispel, and if you take in what I'm about to tell you, you will be a better, stronger, more lean muscle mass athlete. So, a lot to cover. Here we go. Here's a fun little cartoon for you. I guess it is a downside of being so big. Ha ha ha. Here's the outline. Just like we talked about with carbohydrates and fat, we'll follow the same outline for protein. Okay, so basic structure and function. I've tried to put in red the most important stuff because there's so much information. So you only need to be reviewing for your quizzes and your exams what is in red and what I circle or put a star beside. When it comes to protein, it is structurally different from carbohydrates and fat because it contains nitrogen. Carbohydrates and fats contain carbon, hydrogen, and oxygen only. But what makes a protein structurally is the addition of nitrogen. While this makes protein what it is, it also has a lot of drawbacks because that nitrogen can be really tricky for your body to deal with. It's kind of hard to break down if the breakdown product of nitrogen is ammonia, and if that accumulates, it can be really dangerous for our body. It can make our kidneys work really hard. So while we like protein for all the good things that it gives us, structurally, the addition of nitrogen also adds some challenges. Okay, this is just what I said. That nitrogen, even though it makes it what protein is, it makes it really difficult to deal with. So here's a picture of an amino acid. We already remember from our beginning chapters that every protein is structurally made up of smaller components called amino acids. Just like our carbohydrates are made up of smaller components called monosaccharides, just like our dietary fats are made up of smaller components called fatty acids. Well, our proteins are made up of these building blocks, smaller components called amino acid. You can see there where we get the name. Amino means nitrogen containing. You don't need to know that, but that's where it comes from. Some of our proteins will be relatively short chains of amino acids, but other proteins can be really complicated and complex and have thousands of amino acids making it up. You don't need to know that, but I'm just giving you some information. What I would like you to know, however, is that there are 20 total amino acids. That's pretty crazy. All these thousands of amino acid chains that make up all the different proteins we have in our body. Every protein is some combination of those 20 or some of those 20. Here is a picture of an amino acid structure. You do not have to know it. That's what it looks like chemically, fine, good. All I want to point out, check it out. It has nitrogen, N. Carbohydrates and fats do not. Each amino acid has 4 parts. The amine group on the left, the acid group on the right, a carbon in the center. These 3 are the same for every amino acid. But what makes one amino acid different from another is the side chain. I'm not going to ask you specifics about the side chain, but I do want you to know this is what is different between amino acids. If you look at tryptophan versus leucine, they're going to have the same amine group, central carbon, acid group, but what makes leucine different from tryptophan is the side chain. That's it. Just took a drink there, sorry. So here are examples of different amino acids. I would never ask you the specifics about how glycine is different from aspartic acid, is different from phenolphthalein. But all I'm pointing out, what's different is the side chain. Kind of looks like little Tetris pieces, doesn't it? Now, here are the 20 amino acids. You do not have to know all 20. However, being that this course is sports nutrition, I wouldn't be doing my job if I didn't point out leucine. So lysine is also important. That's why I have both of them circled. But the arrow is pointing to leucine because that is going to be our most important amino acid. Why? Because this is what helps to build muscle. Oh man, how cool is that? There's other amino acids that help in the process, but make no mistake, it is leucine. It is leucine that is the most important for muscle protein synthesis, which is just a fancy term for building muscle. Leucine, leucine, leucine. Be careful because it's not lysine. That's important, but leucine, L-E-U. Now, I would like you to know the main breakdown we have, and maybe you've heard of these. I believe I introduced it earlier in this semester. 9 of the 20 amino acids are considered to be essential. Essential means that our body cannot make them. Therefore, it is essential to get these through our diet. It's a little bit weird in how they're termed, but the essential amino acids, 9 out of the 20, know the number 9 and know that they're considered essential. Because our body does not make them for us, it is essential that we get these through our diet, through the food. What do you notice is on that list? Leucine. So when we talk about protein intake, when we talk about the potential for supplementation, which of course we would rather get all the protein we need through our food, but when we talk about bringing in food, we're going to focus on leucine. And therefore, the remaining 11 are considered non-essential. It is not essential that we get them through our diet because our body makes them for us. Holy moly, our body can make these. This is huge. Huge. Our body makes over half of our amino acids. Every cell in your body, folks, a little protein producing factory. It's crazy. Our cells do not make carbohydrates like that. Our cells do not make triglycerides like this. It is protein. Our body makes protein for us. It's a wonderful thing. Some of the textbooks use the words indispensable and dispensable. We're going to focus on essential and non-essential. So in addition to leucine, another one that you may have heard of, you don't need to know this, but have you ever heard of, yes, if you get really tired after Thanksgiving dinner, maybe it's because of the amino acid found in the turkey called tryptophan. But research has shown that your sleepiness is probably due to all the carbohydrates that you ate. So you had a little bit of energy and then you crash. All right, not on the test, but that's an example of an amino acid. And then we've got to talk about leucine, folks. Leucine. I like this table because it gives us an example of foods that are rich in protein. I know it might be kind of hard to see. You have access to this in the PowerPoint, so you can make it bigger. But what I want to point out is the one that is red. This is the amino acid concentration of muscle. All right? And all I'm saying here is that it's best if we can bring in proteins that more closely match the composition of our muscle. This is talking about leucine concentrations, right? So all I'm saying is, on the left, these are the proteins in food that are going to contain leucine. I mean, they all contain some leucine. But I'm not going to ask you bovine milk or casein or beef or whatever, but I'm just saying we can compare the leucine concentration of foods, and it's best, if we want to grow our muscles, it's best if we eat foods that have a leucine concentration similar to muscle. So what do you notice? Whey is an excellent protein source because it has a ton of leucine, which we need to build muscle. And it's on the side here. Everything to the left is what's going to be better for us to eat because its leucine concentration most closely matches that of our muscle. Really cool, isn't it? Okay, a couple other bits on structure. We talked about proteins being amino acids, right? So every protein is simply a chain of amino acids joined together. AA stands for, in this case, amino acid. So sometimes it might be like a linear chain. Sometimes these amino acids kind of fold back on each other. But any way you slice it, every protein is some kind of combination of amino acids. And all we're pointing out here, the types of bonds that join the amino acids are called peptide bonds. You should know that. You don't need to know any more of the specifics, but what connects the amino acids is a peptide bond. Cool. There are different types. Okay, so I am asking you to know some specifics, but I think you can handle it because di as the suffix tells us two. So a dipeptide is when two amino acids are joined together. A tripeptide is when three amino acids are joined together. And a poly means many, are when four or more amino acids are joined together. All right, keep it simple. All right, so now let's switch over to talking about functions. We have a lot of protein. Out of all the macronutrients, it makes up the biggest part of us. I did this before can't remember if it was chapter 2 or chapter 3 or chapter 1 even in this class. Anyway, let's review the functions. You might see the functions listed kind of as muscles, skin, hormones, enzymes, transport, antibodies, but I find it much easier to break it down this way. These are the three main functions of protein. Number one, our proteins are utilized in our body for structure. Of course, muscles. Protein forms muscles. We have over 600 muscles. But it's not just muscles. Protein is the primary component in our skin cells. Protein makes up our hair and nails. Protein makes up tendons and ligaments. These are really important for athletes also. So protein is a huge structural component. That's probably the function that people think of most. But you see, protein does other stuff too. Protein is used to form a whole bunch of chemicals. So there are all these really important chemicals in our body. Make sure you go over some examples. Let's talk about enzymes. Enzymes are needed to speed up chemical reactions. Guess what? Enzymes are structurally made up of protein. Hormones. Think about growth hormone. It's a really important chemical messenger. Tells the muscles to grow. What are hormones made up of structurally? Protein. Antibodies. Part of our immune system to help us fight disease. What is the structural makeup of antibodies? Protein. And there's so much more. Hemoglobin is the protein on the red blood cell surface that transports oxygen. So what I'm saying is we cannot transport oxygen in our blood without Protein, because proteins make up hemoglobin. So that's really, really, really important. And there's more examples. I just listed some. And then, I hope we know by now, folks, protein is our last resort for energy. Maybe, and you should know this number, this range, maybe somewhere between 10 and 15% of all of our energy should come from protein. That's it. We don't want to utilize too much. If we have to utilize more protein for energy, it's going to take away some protein that we would otherwise use for structure and chemicals. Really, really good. So here's more information. Protein is used to make up muscles, ligaments, tendons. There's protein in our bones, the collagen. Protein is in our skin. Hormones, enzymes are made up of protein, antibodies made up of protein, hemoglobin that transports oxygen made up of protein. And then energy, we only use protein to burn for energy as a last resort. Which means, on average, only 10 to 15% of all of our energy is going to come from protein. Carbs and fats are going to make up 85 to 90%. So 85 to 95% of our energy is going to come from carbs and fats. Only 10 to 15 come from protein. That's how it's supposed to be. Okay, moving on here. Dietary recommendations. We already talked about the acceptable macronutrient distribution ranges. That's a mouthful, isn't it? Somewhere between 10 and 35% of all of our daily food should come from protein. You should know that range. Now, protein is the first macronutrient that we're going to be a little bit more specific. So it can also be helpful to give a specific amount of grams that we need per kilogram of body weight. By doing this per kilogram of body weight, this helps us change our needs based on your weight. Someone who's heavier, has more muscle mass, is going to need more protein. So, 0.8 for a sedentary person. You need to know this number. 0.8 grams of protein is needed per kilogram, per kilogram of body weight. All right. Now, we can do the math. And I'm actually going to go get my calculator. So first, we have to convert our body weight in pounds into kilograms. So let's do that. I'll do it in black. You take your weight in pounds, and we divide by 2.2. And that's going to give us our weight in kilograms. Let me go grab my calculator. I'm not going to ask you to calculate this on an exam, but I think it's a good exercise that we can do here. Why not apply this to ourselves? All right, I've got my calculator. Let me go back up to where I've been doing this from. So I will tell you, I'll use myself as an example. I'm about 150 pounds, right? So I take 150 and I divide by 2.2, and that gives me 68 kilograms. So then what do? We take however many kilograms we are in weight, and we multiply it by 0.8. So 68 times 0.8 is 54. So based on this, if I were sedentary, which means I don't do any extra activity, I would need 54 grams of protein per day. Perfect. So for a sedentary person, which, let's be honest, is a lot of Americans, this would be another way to look at their protein recommendations. Now, an athlete, they're going to need more protein. Of course, an athlete's working their muscles, they're breaking them down. We've got to give them protein to build them back up. So we'll talk about that. But we're starting with sedentary, 0.8 grams of protein per kilogram of body weight. Do athletes need more? Yes. However, probably not as much as you think. Okay? Here are some examples. And folks, it's hard because there's not a way to know the exact right amount for each person because we're all different, right? Let me go ahead and change this because, let's see, I like to update the information when we get it. You know, I think the upper limit might be about 2.0 instead of 1.7. Endurance athletes might need to go up a little more. Let's take this to 1.8, maybe 1.8. So it's hard because, you know, we don't know the exact right thing for each person. A lot of it's trial and error. But let me give you a couple things to know. So who's going to need the most protein? What type of athlete would need the most? Well, a strength athlete. This would be a weight lifter. This would be a sprinter. Someone who's doing really high intensity activity for short periods of time. Who's going to need the least? Well, a recreational athlete, a weekend warrior, someone who just goes for a walk every day, right? Let's say overall. So I know it says at the bottom you should have an idea of these ranges, but it's kind of hard because we're still learning. Let's just say overall. Maybe overall, athletes would need somewhere between let's go 1.2 to 2.0 grams. Let's go with that. I think this might be kind of low. So we're constantly learning and doing research and playing with these numbers. But what I'd like you to know is what I've circled in red, right? So you should know who's going to need the most protein out of all the athletes, a strength athlete. Who's going to need the least? Well, someone who's not very athletic. And then overall, for most people who are considered quote-unquote athletes, somewhere between 1.2 to 2.0 grams. So the upper end may not be as high as you think, right? So if we compare it to the sedentary 0.8, that's over twice, right? Yeah, over 2.5 times. So it is a big increase. But remember, our body makes protein for us. So it usually isn't that difficult to meet our protein needs because our body makes them for us. And then a lot of our meals are protein focused. So we don't necessarily need as much as we think. Okay, let's go back to our sample athletes. Here, I've done some math. You don't have to know these, but like I said at the very beginning, I'd like to give you some examples. So Zydrunas, our world's strongest man, 400 pounds, 180 kilos. So I used 1.7. Maybe for him, it might be good to use 2.0, right? 2.0 would be 360 grams. That's a ton. But remember, these recommendations are based on weight. He's a big guy. Someone like a team sport athlete like Mia Hamm, she is smaller. I'd probably bump this up to maybe 1.4, 1.6. Let's split the difference, right? So that might be closer to 70, 72 grams of protein a day. Our endurance athlete, our Ironman, Chris McCormack, he's also pretty lean considering. I'd probably bump this up a little bit. I'd probably say 1.5. So that would be a little bit higher, maybe like 120 grams of protein per day. But I'm just giving you some ballpark ideas, okay? I'm not going to ask you these, but we're just playing out some potential ideas. Now, this is an area of a little bit of conflicting research. We know athletes require more protein, but how much more is in question. Some say a lot, a lot, a lot. So in other words, some say more is better, even if it's like a lot more. Some say, well, you may not need as much as you think. Most researchers believe that about 2 is the upper limit, and that's what I said before. It might go a little bit higher, maybe 2.2, 2.4, but you're not going to go much higher than 2. So let's have you know that for most people, the upper limit would be 2.0 grams of protein per kilogram of body per day. I'm kind of updating based on research. I've been reading more. I think maybe we need a little more. But, it's important that we are able to do that. We're able to take in the latest research and talk about it and then update our guidelines. Okay, if we were, if we were to take in too much protein, right? If you take in over 3 grams a kilogram per body weight per day, it's because of that pesky nitrogen. Remember I said nitrogen is hard to get rid of? So if you bring in extra protein, that pesky nitrogen, it's hard to get rid of. It turns into ammonia. It really makes our kidneys work really, 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 really hard. So it could lead to kidney damage. Sometimes it could also lead to dehydration. But all I want to say here is one of the potential health risks of ingesting too much protein would be effects on the kidney. Excuse me. Now, this doesn't mean that that's going to happen over a 6-month training period. This usually, the kidneys are pretty resourceful, but over years of excessive protein intake, that's when we're going to get into the kidney damage. All right, so I'm going to go through this. I've already talked about it, but I just want to say it again because it's so important. Okay, if protein is so important to the body, we need it for structure, 600 plus muscles, the skin, our largest organ, tendons, ligaments, hair, nails. We need protein for all these important chemicals. Yeah, so why is it that we may only need, somewhere between 50 and 35% from our diet? We need more carbs, 45 to 65%. Many people will need more fat, 20 to 35%. So why is it? If protein is so important to our body, why do we not need to bring in as much through diet to still have as much protein that we need? And it's because our body makes protein for us. I've already said it, protein synthesis, I'm going to say it again. Your body makes 11 out of the 20 amino acids, those non-essential amino acids. Unbelievable, right? Your cells are little protein-producing factories. They make protein, protein, protein all day, all night. So because our cells make some for us, we don't need as much through our diet. So I'm not a protein hater, not at all, but I just am understanding the body, okay? Good. It's so important I made another slide. Ha. Now, what if you bring in more? As I said, it's not difficult in this society, right? It's not difficult at all. Think about the average dinner plate. The average dinner plate, even lunch plate, is protein-centric. There might be some vegetables. It's kind of an afterthought. But the meat or the protein is usually the biggest thing. So it's not hard. Our body makes a lot of amino acids for us, and then we tend to not have any problem at all getting enough protein. So there is a risk. What if we exceed our protein recommendations? Well, can you store it? Not really. You should know this. We can store small amounts, but the body cannot store large amounts of protein. Think about it. We can store large amounts of glycogen and glucose. I bet you have enough glycogen stored in your liver and skeletal muscles to run 20 miles. You do. You have the energy for it. Whether your muscles can do it's a different story. So we can store carbohydrates. We can store fat in our adipose cells. Let's think about the TV show My 600-Pound Life. The body is incredible at its capacity to find places to store fat. So we can store carbs, we can store fat, but we cannot store large amounts of protein. So if we bring in extra protein, well, your body will try and store it, but it can't store much. Your body will try and break it down, But remember, protein is difficult to break down. That stupid nitrogen. So this is a real problem, folks. We can't store large amounts of it. It's difficult to break down. So what if we bring in more protein than we can store? What if we bring in more protein than we can get rid of in a certain given period of time? Well, our body has no choice. The last thing it'll do is turn it into fat. How about that? True story. So some people think they're doing the right thing. You know, they have some knowledge. What do they say? Like, some knowledge is the most dangerous. You have some knowledge. Yeah, okay, I know proteins are important for muscles. But then they don't have the additional knowledge to know that our body makes some protein for us. We don't need as much as you think. And if we bring in extra protein, even though some people think they're doing the right thing, their body may turn it into fat, right? So someone goes to the gym, and then they pound some supplements. Oh, I went to the gym, I need more supplements. And they think they're helping, but it could really be turning the protein into fat. Good stuff. All right. So what I'm going to do is I'm going to stop this first video, and then we'll come back for a second one. See you next time, folks.